Right. Hi, everybody. So, yeah, my name is Cristian Farías from Universidad Católica Temuco, and I'm going to talk to you about the important things like the World Cup. No, really, about Terminator. No, not again. So I'm going to talk to you about Chilean volcanoes and exactly what the earthquakes in the last 12 years have done to them. So this is kind of a very brief review with some of the main results that we have seen throughout the years. And of course, given that I don't have too much time, I'm going to skip a lot of papers. So if somebody knows somebody that is not on the presentation, please, I apologize on advance. So I am from Chile. And given that the World Cup is around, Chile is a country in which we won the first Copa America in 2015. And one thing really interesting happened before we won the Copa America, and that's because Arturo Vidal, the guy over there, actually crashed his Ferrari like 1 week before the final, or 2 weeks before the final. So it was a very bad moment in the history of our country, and afterwards we won it. So basically that leads to an obvious correlation that anytime Arturo Vidal crashes his Ferrari, we are going to win the Copa America. Of course, we know, everybody here knows that correlation is not causation. And that's the story about this talk, about how do we see correlation sometimes. And let's try to understand exactly when we have something and when maybe we don't have too much. So let's go with some global observations. So the Central Chile Volcanic Arc is a place that is really, really, really active, and something really interesting has happened in the last 12 years. The first thing, if we go to the graph over there, to that plot, to the plot on top of to the right. That one, yeah, no. The thing is that we are taking a look at how many eruptions in that portion of the arc we have per year, pretty much. And there is a very interesting contrast, because even though we didn't have any volcano like entering into an eruption right after the 2010 Maule earthquake, we can see that is some kind of sustained activity in terms of eruptions in that particular place of the world. The other thing is that we go to see exactly what happens with the different alerts that the volcanoes have had, or maybe the moments in which volcanoes are not really having an eruption, but really doing something extra, like having a swarm that is interesting, or maybe you have some inflation that is weird. So any type of interesting unrest thing. Yeah, we go to the other plot on the downside of the slide, and we are going to see that many volcanoes actually started doing things after the Maule earthquake, and that has been sustained. So we have, in particular, we have 3 volcanoes. Those 3: Planchón, Peteroa, Nevados de Chillán, and Copahue. Those 3 are in front of a couple of the main patches of sleep of the Maule earthquake. And in the case of Peteroa and Copahue, those volcanoes actually go from being like in a base phase to some unrest, then some eruption, then go back to the base state, then again in unrest, then again to the base phase. So it's so they have been like really active in the last 12 years, and that has been really sustained. Actually, Copahue, the eruption of 2012 has been linked to the Maule earthquake because the static stress change was long enough, was large enough. And Nevados de Chillán, that is in the middle, is a volcano that started an eruption at the beginning of 2016 and has been in an eruption sustainably since then until now. And then we have to, of course, ask, how much of this is really from the earthquake? How much of this is really the volcano doing what the volcano does? And of course, that's difficult to know because we didn't have too much instrumentation on those volcanoes before 2010, but we can still give a couple of ideas. So this is like the very simplified view of what an earthquake does. First, it shakes you. Of course, the waves go through the volcano, and then many things can happen. There might be an interaction between the waves and the fluids there. We can have some overpress. We can create some overpressure in the at some moment. We can also trigger some changes in permeability in faults that can allow actually fluid to go forward afterwards. We also have the deformation that comes from the static stress. That's and that's like the most typical thing we all take a look at the beginning, like how much how's the deformation beneath the volcano? Do we have an opening? Do we have more spaces for magma to go up? Did that change after the earthquake or not? And in the case of 2010 Maui earthquake, we do have some really large variations of static stress, like 1 bars or maybe 1.5 bars at some point. So it's very large, and that's sustained over time. And the third part of the third idea is that the earthquakes can actually generate a deformation on the mantle, and then when we have a viscoelastic relaxation, that the stress transfer can be transferred into the crust, and then we have some other deformations, and then we can explain connections for many decades. That's a bit weird as well, because that's very difficult to prove. But people have suggested it, saying things like that Hudson volcano, on the eruption of Hudson volcano in 1991, might be related with the 1960 earthquake, which is, difficult to prove. But there has been suggestions. So let's see. So what did the Maui earthquake? What happened with the Maui earthquake? One thing that was really important at the beginning was that there was a reference there that is not well put, sorry. So this is the work of Matthew Pritchard, that was published in 2013, and he showed that he and his colleagues shows that there was that many volcanoes on the volcanic arc actually sunk. They were here and then they were there, like for 10 centimeters or even a little bit more, which is really strange. And that happened along the arc. So they were taking a look. They were having this theory that the earthquake actually, what it does is that it promotes fluid motion from one place to another, and then of course the volcano suddenly start to sink a little bit more. Yeah, that could work. And the other part, the other thing that the Maui earthquake did was the static stress transfer, and that's why I'm putting Copawe there, because that's one of the volcanoes who suffer the largest static stress transfer of the whole arc. So that's a sustained effect over time. And here's Jaima, and this is some work in progress that I want to show you because it's under review right now. Here's Jaima, and Jaima is one of the most active volcanoes in Chile. Nevertheless, after the Maui earthquake, this is one of the most quiet volcanoes in Chile. Actually, we're kind of thinking on level the volcano like a mountain instead of a volcano because it's so quiet in the last 10 years. Nothing really has happened on Jaima, like even on seismicity. And apparently what happened there is that the earthquake actually affected the earthquake, well, with the static stress transfer actually affected the different magma pathways, like closing the magma pathway that goes from the deeper parts of the crust up to the shallower parts, and the ones that go from where it might be a storage up to the really shallower part, to the surface, which kind of shows you a very interesting behavior, because we are not thinking anymore about volcanoes that erupt after an earthquake, but rather volcanoes that respond to an earthquake in a very different way. So then the complexities of the responses actually increase, and you have this wide array of many different things that can happen. Another thing is the Yapel earthquake. Yapel earthquake was an 8.3 earthquake that came with a tsunami, but at least from what I am doing, for what I am interested on, the really important and curious behavior was what happened with the Chilean, Copawe, and Villarrica. Those volcanoes are located 500 kilometers away, 650 kilometers away, and 800 kilometers away from the eruptor zone. And what we saw was that in the case of Nevados de Chillán, there was, oh, sorry, this is here. In the case of Nevados de Chillán, at the beginning, we saw a change in the way of the, on the seismicity that was linked to the fluid dynamics. And that was sustained over time. So it was triggered by the passage of the waves, but then the volcano was unstable and more unstable over time. And then a couple of months after, we have an eruption that has been sustained since then up to now. And we have a Copahue volcano that right after the earthquake, it had a swarm that lasted for 10 days pretty much. And then we have an eruption 2 weeks after the earthquake. But again, Copahue is 650 kilometers away from the earthquake, so it's a long distance. And also we saw something on Villarrica. First, a small activation of the on the signals that are linked to the fluid dynamics, and then some period of quiet. Some small period of quietness that was that we saw it on the deformation data. So again, very sensitive volcanoes. Why are they so sensitive? And apparently, one of the things that might help us to understand exactly why they can be so sensitive is because of the fault systems. The fault systems are the ones that actually are going to allow or not that for fluid to go from the deeper parts of the crust up to the surface. And of course, we don't have only one fault that is linked to these motions. Really, we have a very complex system of faults that can play that role. So then the question may be that maybe what happens in reality if the earthquake doesn't really affect the volcanoes by themselves, but rather it affects the faults. It affects how it affects the pathways for magma or even water, if you like, to go up. So then that might help us to understand, for example, why there are some volcanoes that react a lot, because they are the ones that are more active, and then that are a little bit more open in a couple of structures that can serve as magma pathway, for example, rather than other ones who are not in that period of their lives, pretty much. So we are thinking on that, and then if we want to prove that, yeah, we need to model. That's one part. In the case of the Yapel earthquake, we showed with our numerical models that in fact the structures that got the larger openings during the shaking were in fact the ones that are more linked to the fluid motion afterwards. So that's a good example. Well, also, sure, and also the same thing, we showed the thing that happened with Jaima volcano. But in order to prove everything up, we need to take a look, a closer look at this. Problem is that it's not only based on structural geology, because the seismicity doesn't often shows more structures that are not really visible on the surface. So we need to put many different arrays. We need to put arrays in places that we're not thinking before. For example, in between volcanoes or a little bit further away from the volcanoes. And I wanted to close with this thing. It's the distribution of seismicity in Copahue volcano, because we are doing this just right now as we are speaking. We can identify different sections or clusters of seismicity in a volcano like Copahue. And we can see that if we go into take a look at the energy release on those structures and even on the V values of those structures, or the seismicity of the structures, they don't behave the same. But rather we have some cascading effect. Something happens in one place and then it has a response. That's really interesting. So we really need to take a look at what happens on the faults. So if we want to understand why a volcano can be sensitive, why an earthquake can produce an effect, we need to take a look at both the source, which is the earthquake, of course, and then we need to take a look at the structural side of the volcano, and we need to have a lot of measurements and models done with the faults. Thank you very much.